Hello, my name is Saeed Fatullahzadeh and I'm a PhD student at the Concordia University. I'm excited to present CatDB, an LLM-based framework for generating data-centric ML pipelines. This novel approach integrates large language model to automate the creation of high-quality ML pipeline. Specifically, our method enables end-to-end pipeline generation by leveraging structured data catalog to guide LLM decisions. This talk will have two parts. In the first part, I will present the background of the CatDB, and in the second part, I will demonstrate CatDB in action. Imagine an end user or data scientist analyzing a domain-specific data set without being a domain expert. Given a tabular data set represented in a single or multiple files and an ML task such as classification or regression. Our goal is to build data-centric ML pipeline. CatDB focused on profiling domain-specific dataset, precisely filtering and projecting metadata, and utilizing LLM to generate ML pipelines. We have broken down the generation process step by step. The main prerequisite is building a catalog, followed by refinement. The data catalog materializes metadata from each column individually, include table and column names, statistical values for numerical columns, and more. Additionally, generated general metadata such as number of rows, columns, and the datasets physical paths is also materialized. The data catalog steps include two sub-refinement tasks. Task A, we need to precisely annotate the feature types. In task B, we need to deduplicate categorical feature values semantically. These two tasks are necessary because the data profiling tools cannot identify them correctly. This refined catalog significantly enhances the accuracy and effectiveness of the generated ML pipelines. With metadata in hand, we constructed a context-aware prompt using a template specific to an LLM. First, we infer instructions essential for the ML pipelines. For instance, if certain features contain missing values, we add an imputation rule to the prompt. Second, we include the metadata related to inferred rules to guide the LLM in making precise decisions. Finally, all this information is combined into a single prompt using a structured template. The final steps involve interactively communicating with the LLM to generate and execute the ML pipeline. CatDB provides a simple API called generated pipelines that handle this interaction seamlessly. Additionally, CatDB includes a robust self-error correction mechanism. It automatically detects and corrects various errors, include semantic, syntactic, and runtime errors. For the syntax errors, incorrect Python syntax or missing import, or it automatically corrected or resubmitted to the LLM for correction. For the runtime errors, issues such as incorrect features, transformation, or incompatible data types are identified during the pipeline execution. CatDB iteratively refined the pipelines, ensuring the successful execution. This comprehensive error management ensures that the generated pipeline are robust, executable, and reliable. As a toy example, we would like to compare the pipeline that generated by the state-of-the-art systems such as AutoML tools and Microsoft AutoGen against CatDB. In this example, we use the salary dataset, and our goal is to predict the salary feature as a regression task. More importantly, features like experience and gender contain semantically duplicate data. The skill feature has a list data type and address is a mixed type feature. So the baseline systems follow three steps: loading the dataset, hashing a categorical features where only the gender feature is identified and as categorical, and the model building. As you can see, the majority of the pre-processing steps are missed due to the dataset contain semantically duplicated data and unclear feature types. On the other hand, we have 7 steps assembled by CatDB instructions. After loading a dataset, feature values are deduplicated and annotated as categorical feature in step 2. The address feature is decomposed and skill feature is annotated as a list type. All of these major pre-processing steps improve the data quality and have a significant impact on the model performance. As you can see, the model accuracy in CatDB is 91.8%, which is much higher than the baseline accuracy of 39.2%. Now let's see CatDB in action. CatDB is open source and the source code available at this link. For any questions, feel free to send me an email. After installing the necessary requirement, we configure the LLM by specifying the model name, API keys, and number of iterations for generating the pipelines. We begin the preparing the datasets, splitting the data into the training and test sets while defining the ML task. For example, a binary classification task, we predict the income attribute in the adult dataset. The prepared dataset then submitted to Build Catalog API. For debugging purpose, CatDB creates a report API visualizing a data catalog information. It contains 5 diagrams that shows details such as a dataset overview, feature types, a statistical overview of the missing and distinct values, and the frequency of the categorical features. Finally, CatDB automatically generates pipelines by data catalog and LLM configuration. The API execution time depends on the dataset size and the number of iterations. The pipeline analysis tab includes runtime, performance, cost, and error details. Additionally, it presents system and catalog prompts in a hierarchical tree format. As shown, the system prompt contains the task, dataset descriptions, infer rules corresponding to catalog data displayed below. The source code of the generated pipelines can be viewed in the SRC tabs. Since we set the number of iterations to 7, different pipeline versions are available for each iteration. Each pipeline followed all key steps include pre-processing, feature engineering, and model selection, and report the performance metrics. As we have mentioned frequently, LLM-based systems often struggle with the hallucination. Our CatDB system also face these challenges, but we address it using 2 key solutions. We defined explicit rules for the LLM and instructed it to perform tasks very precisely. We implemented a mechanism to generate multiple pipeline candidates for the given dataset. The final decision is made by the executing each pipeline on a sample set, which contain only 10% of the total dataset. Based on the result, we then selected the optimal pipeline. Of course, preventing the hallucination is costly. As a future work, we plan to mitigate this issue in a smarter and more efficient way. Thank you so much.